Start.
Yes, sir. Start.
Okay.
আচ্ছা স্টার্ট করি।
Okay. Hmm. Can you see the slides, right?
Yes, sir.
Okay. So now, next topic of discussion is my stagnation properties in a fluid. Now, what you know about the stagnation term? I think you have used this term earlier in thermodynamics. What do you know about the stagnation term? Any idea? What do you mean by stagnation? Anyone?
Sir, properties of a fluid at a particular instant of their means the external things that are acting on it. For example, the pressure or the density.
No,
That is
no, no.
Sir, when
Stagnation
stagnation
properties.
means when water is stored or water is not moving at all.
Yes,
It is
something
at
like
one
that.
position. Yes.
Properties means stagnation. Properties means what? Properties may be anything. Properties may be temperature, maybe pressure, whatever. But what do you know about the stagnation condition of this term? Stagnation is a condition. Okay, stagnation means whenever I am having my medium at rest, suddenly it is say for example, it is at rest. That means my velocity is zero. When my fluid comes to rest, okay, then that condition is known as your stagnation. And at that point of time, that means at that point, at that stagnation condition, whatever the properties the fluid contain, that those properties are known as your stagnation properties. Is that clear? I'm giving you a practical example. Say you are having a flow, just a water flow, okay, just at a particular velocity, and you are putting a, say, a metallic plate, just you are putting a metallic plate inside that flow. So what is happening just in front of the fluid molecules or the water molecules which is coming, so it will be suddenly come at rest in front of that metallic plate or not? It will come at the rest, okay, suddenly, right?
Yes, sir.
So that type of condition, that means whenever I'm taking some fluid, okay, some, that means what, or the whole medium, whatever it is, whenever it is coming at rest or my velocity is zero, that condition is known as your stagnation. And at that position, whatever the properties you are having, it may be temperature, it may be pressure, it may be enthalpy, okay, whatever, those properties are known as your stagnation properties of that fluid. Okay. So it is written over here. I think in general, stagnation point in a fluid is a point in which it is brought to be at rest, okay, so that the velocity at that point is zero. This is a very simple definition. In general, that is the definition of any stagnation condition. So different properties at that point then called as stagnation properties. So different properties may be present, okay. So those properties are known as your stagnation properties. And how to denote these properties? There is a common way to denote, basically suffix zero, that means, or not, whatever we call T suffix zero or T naught, whatever we call H suffix zero, or your H naught, that is your enthalpy. Okay, so this suffix zero or the naught, that is your stagnation, that is the notation of the stagnation properties. Say for example, you are having a arrangement like this, and say at this position we are just bringing this fluid to rest suddenly. So that is, say this is my inlet, this is my outlet. So at this position, basically, that will be my fluid will come to the stagnation state, basically. That state is known as your stagnation state. This is some obstacle we are putting, say, and we are considering, okay, that at this position my fluid is at my stagnation state. So as I can apply the steady flow energy equation, so I am applying that same. You have studied this equation. I think I don't need to explain each and every term, because this is for the inlet, this is for the outlet. This equation is nothing but SFEE, steady flow energy equation. If you recapitulate, this is nothing but my steady flow energy equation, the general equation. Okay. Now different terms may be zero depending on the situation. So now here you see, if I simplify this here, as this is insulated, I am considering, okay. So this QCV, that means heat given into the system, that means this is zero. Work output from the system is my zero, because not I am not getting anything, any mechanical work, okay, from this control volume. So that is my zero, and you can see it is in the same elevation. So Z term is also same, okay. Mass flow rate is same, inlet and outlet, obviously that should be same, okay. inlet to the outlet. So this is my basically simplified equation. H suffix I means the inlet, okay. Suffix E means my exit, okay. E stands for exit. So Hi plus Ui square by 2, Ui is the velocity at inlet, Ue is the velocity at the outlet, okay. You are at the exit. So this is the simplified equation from the steady flow energy equation. Hi plus Ui square by 2 is equals to He plus Ue square by 2. So here you see H plus U square by 2. That means if I just consider that this is my, say, your just whenever I am just putting this obstacle, what will happen? Obviously, as I told, that this is going to be my stagnation state. Here my stagnation state is going to occur. So then there will be some inlet energy, there will be some inlet velocity. So that is my Hi. I am simplifying that H, and Ui I am simplifying that to U. What will happen to this terms on the right hand side whenever I am putting this obstacle? Basically, I have to denote the what? I have to denote the stagnation properties over here. So He will be obviously converted to Ho, because H suffix O stands for my stagnation enthalpy. This is called H suffix O is known as your stagnation enthalpy. And why this term is 0? Because why this term is 0?
So U is 0 there.
U is 0
So because
because
at
that is the
zero
concept of
at rest.
stagnation. That is the concept of stagnation state. There is no velocity as I'm putting the obstacle over here. So that's why this part is 0. So this is the simplified equation of the stagnation enthalpy. H naught is equals to H plus E square by 2. These are the inlet your properties. Okay. So
Sir,
H is
what
the
is H naught stands for? What does H naught stand for?
H naught means this one. H naught means my stagnation enthalpy. This H suffix 0 is called as H naught basically. Okay, that's why I'm calling as
Okay, sir. Okay.
H naught. Okay, H naught. Some people say it as your H suffix 0. Okay, but that is not a technical call. Basically, I should say it is called as H naught or H0 if you can call. Okay. So actually H suffix 0. Okay, so this H naught is basically the stagnation enthalpy. So H is the enthalpy at any position. It may be inlet at any position. If I take here, it is my inlet, and where H is the okay, here they have written H is the enthalpy at any position. I have written that means here it was Hi. Okay, if I want to specify Hi, I can also write Hi. That is not an issue. But in general, if I want to write any position at this position, because this flow is coming at this position, obviously that will be not Hi. That may be something different. That is H. So I can apply at your any position over here. But here at this state, at the stagnation state, obviously my enthalpy will be H naught, and H naught is the stagnation enthalpy. Okay. So this thing I have got from the simplified form. Just I am getting from the steady flow energy equation, applying the concept of stagnation. Now from the ideal gas, for the ideal gas we know dH is equals to Cp dt, very well known equation. Okay, dH is equals to Cp dt, change in enthalpy. Cp is the specific heat at constant pressure, dt is the change in temperature. So I can write this as like this or not. That means, say for here I am having enthalpy H, here I am having enthalpy at your H naught. Okay, that is my stagnation enthalpy. So dH means my H minus H naught. Okay, Cp into dt will be obviously similarly by analogy I can write T minus T naught. What is T naught? What is T naught? What it should be called?
There's temperature at rest or at stagnation.
That means it is called stagnation temperature. It is simply called stagnation temperature. Like it is called H naught is called stagnation enthalpy, T naught is called stagnation temperature. Is that clear? Is
Yes,
that clear?
yes, sir.
Okay. So
Yes,
it is
sir.
similarly. That means if I write P0, P suffix 0, that is called stagnation pressure, like that. So H minus H naught is equals to Cp into T minus T naught. Now you see I am replacing something. That means Cp into T minus T naught I am keeping it as it is. And if this H minus H naught I am taking to the right hand side, basically it will be getting H naught minus H basically. So H naught minus H I can write from this equation as U square by 2. H naught minus H is nothing but U square by 2. Okay, from this equation. Okay, is it clear? It is very clear from this equation that H naught minus H is equals to U square by 2. So that term I have just put it over here. H U square by 2 is equals to 0. Keep this as equation number 1. Now we also know from the basic definition of the Mach number M is equals to your U by C. Okay, that we know. So U square is equals to M square C square. I can just cross multiply, and if I square both the sides, I can write this. Now u square is equals to m square into c square. C square means gamma RT. C is equals to under root gamma RT. So here I am considering that my flow is my isentropic flow, and that's why I am writing this. C square is equals to gamma RT. We are considering that this flow is my isentropic flow, and I can write this. U square is equals to m square gamma RT, because C is equals to under root gamma RT, and C square is equals to gamma RT. Now Cp, we all know this is the Cp, the relation between Cp, gamma and R, because Cp is equals to gamma R by gamma minus 1. From where I can get this one? Who can tell me? Cp is equals to gamma R by gamma minus 1. From which two equations I can write this? These are some very, very basic thermodynamics. Can you hear my voice? Hello?
No, so not remembering, sir.
Okay, so Cp minus Cv is equals to R, you know? Cp minus Cv
Yes,
is
sir.
equals to R, you
Yes,
know?
sir.
Cp by Cv is equals to gamma, you know? Just combine those two equations. You will
Yeah.
get this equation.
Exactly, sir.
You will get this equation. Okay? Very simple. Cp by Cv is equals to gamma. You know that. Cp minus Cv is equals to your R. You just combine. Okay? Replace the Cv and you will get this one. Cp is equals to gamma R by gamma minus 1. Why I have written? Because directly I have written, because these things it is expected that you know. That's why directly I have written, and that thing will be used over here. So now see, if I use this one, this term, where I will use, obviously over here I will use. Okay, so Cp here I am having Cp, I am replacing that by gamma R by gamma minus 1, and here you see T minus T0 is there. I have written T0 minus T. Then obviously I will get a minus. So that's why this term I have taken to the right hand side, because I am getting a minus. Okay, so T0 minus T I am written. So I have written T0 minus T. That's why I have taken this term on the right hand side. Now U square I have replaced by m square gamma RT. Keep it as equation number 3. Okay, up to this any doubt? Up to this any doubt?
No doubt.
Okay, so this equation, if up to this it is clear, this one I will simplify more on the next slide. So you see, from equation number 1 I can write this one. Which one was equation number 1? This one was equation number 1, right? This one was equation number 1. Okay, so from this equation you see I can write this one. T0 is equals to, just if I simplify that, T0 is equals to T plus U square by 2Cp. Just I'm simplifying, nothing else, nothing new I have done. So T0 is equals to T plus U square by 2Cp. Okay, so this is basically the expression of stagnation temperature, which is a property. Okay, and at any point it is dependent on the process, you see. Okay, it is independent of the process, sorry, it is independent of the process, because Cp is a constant. Okay, and this is the temperature and the velocity, nothing else. So whatever the process I should have, this expression of T0, obviously it will be like this. Okay, so this is my expression of the stagnation temperature. T0 is equals to T plus U square by 2Cp. Now from equation number 3, I am just again showing you equation number 3. Just can you tell me what is the difference between equation number 1 and 3? What modification extra I have done in the equation 1 and 3? Anyone? Equation number 1 and 3, what is the difference?
Sir, you have just replaced Cp by gamma R by gamma
Yes,
minus
that
1,
is okay. And
equation 2 you have applied. Equation 2
this
you
one
have
also I
applied.
have applied.
U square
Yes,
is
this one also I have applied. And this gamma T, when I can write for a isentropic flow or not?
Yes, sir. Yes, sir.
So this equation number 3 is not valid for any process, but equation number 1 is valid for any process. Am I correct? Equation number
Yes,
1 is valid for any process. I have not specified the process, but in equation number 3, what is the process? It is the isentropic flow. My flow type is my isentropic flow. That is the difference between equation number 1 and 3. Okay, so that point should be clear to you. So from this equation number 3, what I am writing, that I am going to show you on the next part. So from the equation number 3, I have just you simplified that, and just I have got this type of expression. T0 by T is equals to 1 plus gamma minus 2 into m square. Just you simplify that, you will get it. So T0 by T is equals to 1 plus gamma minus 1 by 2 into m square. Okay. But equation number 1 I have, that's why I can write over here independent of the process. But here I cannot say that independent of the process. I should say it is valid for isentropic flow, isentropic process, or reversible additive process. So that's why it is for isentropic flow. Up to this, clear these two things, equation number 1 and 3. All of you, only Alok is
Yes, sir.
responding.
Yes, sir.
Yes, sir.
Okay.
Yeah.
So for isentropic process, again I know P2 by P1 is equals to T2 by T1 to the power gamma by gamma minus 1. Okay. Again, I am not going to in details of that because this is well known to you from any adiabatic process. P V to the power gamma, P1 V1 to the power gamma is equals to P2 V2 P2 V2 to the power gamma. So if you from there, if you replace the V by T, then obviously you will get this. If you take the ratio, you will get P2 by P1 is equals to T2 by T1 to the power gamma by gamma minus 1. So now by analogy, I can write this or not. P2 by P1, P1 say the initial state, P2 if P2, that means the final state, if it is my stagnation state, I can write this one. The same equation will be only in place of P2 or T2, I will write P0 or P0 and T0. Okay. Can I write this equation? Can I write this?
Yes, sir. Yes, sir.
So just by analogy I can write. Okay. So P0 by P1 or P0 by P1 is equals to T0 by T1 to the power gamma by gamma minus 1. Now this T0 by T1 is what? T0 by T1 is nothing but this one for isentropic flow. T0 by T1 means 1 plus gamma minus 2 by m square. Just you replace that. So here you see only your Mach number is there. Okay, and gamma is there. Gamma is a property. Mach number is a for a particular flow there should be some Mach number. So 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1. The power is as it is. So this is the expression of P0 by P1. Okay. So this is, I have enlarged that. Basically, this is the relation between the stagnation pressure and the Mach number. Take a note of this equation. This equation may be required just in between in your any problem while you will solve it. Okay, for any compressible flow. P0 by P1 is equals to 1 plus gamma minus 1 by 2 into m square whole to the power gamma by gamma minus 1. Up to this, clear?
Yes, sir.
Yes, sir.
Okay. Now here you see this equation also may be used for isentropic flow. This equation also may be used because this inner term inside the bracket, that is your T0 by T basically. So T0 by T1 or T0 by T is equals to your 1 plus gamma minus 1 by 2 into m square. That also may be required. And this is the pressure. Okay, relation between the stagnation pressure and the Mach number. Now we will discuss something about isentropic flow. Now see, just I am sticking to your which type of flow? Isentropic flow. So isentropic flow through a variable area duct. Okay, that I am going to discuss. Okay, so isentropic flow through a variable area duct. Variable area duct means it may be nozzle, it may be diffuser. Those definitions will come now gradually. Okay, what is called nozzle and what will happen to the nozzle, what will happen to the diffuser, depending on and obviously some from some mathematical point of view, obviously. So the isentropic flow through a variable area duct, what should be the case now? First we will go for the mathematics. Okay, so continuity equation, I will apply the continuity equation that is well known to me, that is by rho AU is equals to your constant. Okay. So from this equation I can write this ln rho, just it is simple mathematics, just follow me, you will get something at the end. So your ln rho plus your ln A plus ln U is equals to your constant. Just I am taking log. Then I am differentiating it. What I am getting, d rho by rho plus dA by A plus du by U obviously should be equals to your 0. Okay. Now d rho, I am segregating this d rho term. D rho is equals to your what? This dA by A plus du by U. I am taking this into the right hand side. Rho is the density, A is the area, U is the velocity. I am not repeating, these are some common terminologies, that's why I am not telling in each and every step. So d rho is equals to your minus, because this term I have taken to the right, so minus rho into dA by A plus du by u. Okay, keep it as equation number 1. Now from Euler's equation I can write this one. I think in the very first class of the compressible flow I have used this equation, so it is not new to you. dP by rho is equal, plus u du is equals to your 0. Can you recapitulate this equation, Euler's equation?
Yes, sir.
Okay, thank you. So this dP by rho I have used earlier also in the first class of the compressible flow. dP by rho plus u du, because when now sir, now these questions may come into your mind that why sir is that means from where sir is thinking that I have to use this particular equation. Concept is very simple. Whenever you see here there is no term of pressure, whenever I have to take some term of pressure I have to go for the Euler's equation. That is the governing equation for any fluid mechanics. Okay, that I know. That means from this Euler's equation I have got the Bernoulli's equation and all. So whenever I have to take some change of pressure and those things in any derivation, you always you try to correlate that from this point of view of the fluid mechanics, that is the Euler's equation. So that's why I'm taking this your Euler's equation. So dP by rho, here I am having the pressure term as well as the velocity term. So dP by rho is plus u du is equals to 0. I am simplifying that. dP is equals to minus rho u du, because u du term I have taken to the right. So dP, I am modifying this a bit. How I am modifying? dP by u square. Okay. Why I am modifying this like this? dP by u square, I am dividing by u square on both the sides. Minus rho into du by u, because I am getting this term du by u. Okay, that's why I am dividing by u square over here. Okay, so this is my equation number 1. This is my equation number 2. Now I am doing what? Equation number 2 by equation number 1. What I will get? If I divide this equation number 2 divided by equation number 1, what I will get on the left hand side? Tell me. On the left hand side, what I will get? Equation number 2 by 1. dP d rho or not? dP by d rho and 1 by u square will be there.
Yes, sir. 1 by u square dP by
Yes,
d.
1 by u square dP by d rho. Left hand side is very simple. What I am having on the right hand side? This, you see there is a negative. Here also I am having one negative, so that minus sign will cancel out. So here rho will also cancel out. You can see here I am having also rho. Here I am also having rho. So du by u divided by dA by A plus du by u. Okay. So this term I will get. Now we also know this term. What is this term? dP by d rho. This dP by d rho means c square or not? Because c is equals to under root dP d rho. This is the in general equation I know, isn't it? So c is equals to under root dP d rho. So from that, if I put that, it will be by c square. So c square by u square. C square by u square means 1 by m square or not? Because m Mach number is equals to u by c. Okay, Mach number is equals to u by c. So here I am having on the left hand side c square by u square. Okay, so it is my 1 by m square is equals to the right hand side is as it is. So from this I am again cross multiplying. What I am getting? dA by A plus du by u is equals to m square into du by u. Okay. Now again I can take common. You can see on the left hand side also I am having du by u. On the right hand side also I am having du by u. Finally I am getting what equation? I am getting dA by A is equals to m square minus 1 into du by u. Up to this, is there any doubt? This is a simple mathematics, and where you have to apply these two things, you have to apply continuity equation and the Euler's equation. So this is the area. Here I am. This is the relation between what? Area and the velocity, and Mach number is there. So dA by A is equals to m square minus 1 into du by u. Clear up to this, all of you?
Yes, sir.
Yes, sir.
Okay. So this is basically the mathematics I know, but there is a huge significance of this last highlighted equation that I have written, that dA by A is equals to m square minus 1 into du by u. There is a huge significance, physical significance of this equation for the any variable area duct. dA by A means what? Obviously there is some change in area. Okay, that's why we have generated this type of equation. Okay, so let us see that now. Now that thing is continuing isentropic flow to a variable area duct, and we have got this equation. What is written over here? when m is equals to 1, when the Mach number is equals to 1, if I am having that sonic condition, when Mach number is equals to 1 means sonic condition, isn't it? Mach number 1 means what?
Yes, sir. Sonic condition.
Sonic condition, right? So if I'm putting m is equals to 1, this dA by A is equals just is this term is getting 0 or not? Because right hand side I'm having 0. So if we want to achieve sonic condition mathematically, it may be at maximum or minimum area of the duct. dA by A, say I'm having some expression of A area, cross sectional area, as it is a variable area duct, obviously the area is changing. Say for x-axis, just I'm considering in x direction, I'm having the length of the duct, okay, and if the cross section is a function of that x, okay, if the cross section of that duct, area of duct, which is varying, which is some function of x, and if I am having this term dA by A is equals to 0, from the concept of basic derivatives, what I should say mathematically? First derivative 0 means the mathematically it may be at maximum or minimum area of the duct, isn't it? From the mathematics, I can say it or not.
Yes, sir. Yes, sir.
But practically it happens at the minimum area. Practically there is a term, I think you have heard that term, that term is known as your throat. Throat of any duct. Throat means the minimum cross-sectional area of any duct is called as a throat. So this Mach number is equals to 1 will always occur where? At the minimum area, practically. Okay, I will discuss more on this part. Take a note of this line. Practically it happens at minimum area. I'll discuss more on this. Okay, but as of now, mathematically it may be at maximum area or the minimum area, but practically it happens at the throat. Which condition? Sonic condition. That is the Mach number is equals to 1. Now say I am having two cases. Okay, I may have two cases where this dA by A is for this duct. This is the inlet. This arrow is the direction of the flow, and this dA by A is equals to your greater than equals to 0 over here, and dA by A is less than equals to 0 over here. This is a divergent duct. This is a convergent duct that you can see very easily. But here now the concept of nozzle will come now. You see, nozzle is what? Nozzle is a duct which increases the velocity at the expense of pressure. This is the basic definition of the nozzle. If anyone asks you what is nozzle, what you should say? What is nozzle? Nozzle is a duct which increases the velocity at the expense of pressure. Is that clear? The first line, nozzle, the velocity will be increased, okay, and the pressure will be decreased. At the expense of pressure means the pressure will be decreased. But always reduction in area of the duct does not imply increase in velocity. Have you understood the second line? I repeat, always reduction in area of the duct does not imply increase in velocity. Reduction in area means this convergent. Okay, if I am having convergent duct, always does not mean it is a nozzle. Why? Because if the flow is incompressible, then it is true. If the flow is incompressible, that means in fluid mechanics several times you have used this term nozzle. Okay, so if it is my incompressible, that means if I am having a liquid, then it is true. That means I am having some converging duct, that means it is my nozzle. It is true. But for compressible flow, density is another factor. Why it is written density is another factor? Because if you just recapitulate the continuity equation, it was the main continuity equation was rho 1 A1 V1 is equals to rho 2 A2 V2. Fine. Can you hear me, all of you? Hello?
Yes, sir.
Yes,
Okay.
sir.
So
Yes, sir.
rho 1
Yes, sir.
A1 V1 is
sir.
equals to rho 2 A2 V2. But in case of incompressible flow, rho was constant, so rho cancel out. So A1 V1 is equals to A2 V2. That was the equation for incompressible flow. Okay. Now obviously, if A1 V1 is equals to A2 V2, if this is my equation, A1 V1 is equals to A2 V2, then if the just at the outlet, if the area, that means A2 decreases, obviously the V2 should increase. That is true. That's why it is true. If my at the outlet A2 is less, then obviously V2 should be higher. Okay, then only the term your A1 V1 should be equals to your A2 V2. But for compressible flow, density is another factor. That means there rho 1 A1 V1 is equals to your rho 2 A2 V2. You cannot cancel or you cannot ignore that change in rho. or change in density. That's why it may not be true. Always converging duct means nozzle. It is not true for compressible flow. Okay, so if A increases, that means if area increases, you may also decrease, you may increase also. I'm not saying always that convergent duct will mean that it is not a nozzle. No, that means area increases. If area increases, that means if area increases, that means area increases, they have written, that means I have written area in, that means for divergent duct you may increase or decrease depending on what, depending on the value of Mach number. Here the concept of Mach number is very important. Depending on the Mach number, basically Mach number actually takes account of the sonic velocity. Sonic velocity takes account of the change in density. That is the relation basically. Okay, so how the density is related to Mach number? Mach number is related to basically sonic velocity. Sonic velocity is related to the change in density basically. The expression of the sonic velocity is coming from the change in density, whatever I have shown in the last two slides. So basically it will depend, if the area increasing, it will act like a nozzle or it will act like a diffuser. That depends on the value of Mach number, and the reverse effect will be for the diffuser obviously. So nozzle and diffuser, that case may be different depending on the value of Mach number. So now let us, now I know there is some interest in your mind that how we can decide these things, right? This question run in your mind or not, how I can decide now, okay, when I can call as a nozzle, or when I can call as a this type of duct as a diffuser. Okay, so that thing let us discuss now. So you see, let us take example of this one first. Okay, these two are the cases. This is the equation always I have to see, okay, that I have derived. dA by A is equals to m square minus 1 into du by u. This is the equation that I have derived. Okay, I have to take a bit help from this equation. That's why I have mentioned in this slide also. So now see, if Mach number is greater than 1, if this is the case, Mach number is greater than 1 means my flow is supersonic. Okay, my flow is supersonic flow. Then if my Mach number is greater than 1, that means here mathematically, now parallelly you have to think about the mathematics also. If Mach number is greater than 1, here you see this equation, m square is there, Mach number greater than 1. So if area decreases, that means if left hand side decreases, if this left hand side decreases and m is greater than 1, that means I am having some positive amount over here inside the bracket, m square minus 1, I will have some positive value. So if this area decreases, this part if decreases, obviously the velocity should decrease or not, to equate the both sides.
Yes, sir. Definitely, sir.
That is very definite. I am repeating, those who have not understood, please try to listen very carefully. M square minus 1 is there, m is greater than 1, that means this inside this bracket, whatever term I am having, that is having some positive value, that is having some value. That means if dA by A, if this side is decreasing, obviously this will also decrease. So dA by A decreasing means, say this is this one, that is my convergent, area is gradually decreasing, this one, okay, see my cursor, this one, convergent duct. So convergent duct, and my velocity is, what is happening, velocity is decreasing or not. That means if the flow is supersonic and if the area of the duct decreases, that means if it is converging, then velocity decreases. Velocity decreases means it is a nozzle or a diffuser. Velocity decreases means it's a nozzle or a diffuser.
Sir, it's a diffuser.
It's a diffuser. It's not a nozzle. So by concept, what is nozzle? Nozzle means obviously my velocity should increase at the expense of your pressure. That means my velocity should increase. But here it is my convergent duct. But what is happening to the velocity? Velocity is decreasing. Unlike incompressible flow, it is written in the bracket, you can see. That is the difference between the case of the compressible flow and the incompressible flow. So here the duct looks like a nozzle. It looks like a nozzle or not? By your rough concept, whatever you are having,
Yes, sir.
this
Yes.
duct looks like a nozzle. But if this condition is given, I am having some supersonic flow. That means Mach number is greater than 1. This acts as a diffuser, not like a nozzle. That means at the outlet I will have some less velocity compared to the inlet. This thing is clear to all of you or not? Tell me. Very important concept. Very important concept.
Yes, sir.
Others?
আবার একটু রিপিট করে দিন।
আচ্ছা কোন খানটা বুঝতে পারছিস না বল, try to follow me gradually. This equation you can see with this.
Yes, sir.
Okay, now here if we put m greater than 1, what will happen? This m square minus 1, this term is having some positive value, right? If m is greater than 1, m square minus will have some positive value over here. So if dA by a, now if some value, say for example 2, I am having 2 over here, say for example, or 3, I am having 3. So if now if in the equation, if I am decreasing this left hand side, this du by u will decrease or increase? Obviously it should decrease to get this equation correct, to be the equation correct.
Yes.
Obviously if I decrease, or say for the vice versa, if I increase the area, if I increase, obviously u will increase, isn't it? So here I have written for the decrease case, if area decreases, that means if this left hand side decreases, obviously the right hand side should decrease. So that means if the flow is supersonic and if the area of the duct decreases, velocity decreases. Now the velocity decreases means it is my not a nozzle, it is my diffuser. Okay, so the duct looks like a nozzle, this duct looks like a nozzle, but it is not a nozzle. If I am having this case, if I am having a supersonic flow, this duct will act like a diffuser. Clear?
Yes, sir. Clear.
Okay. If I am having the reverse case, say for example Mach number is less than 1. So Mach number is less than 1. So whatever I am having this m square minus 1, if Mach number is less than 1, I will have some lesser term over here. Okay, so that will be just be the vice versa. That means if the area decreases, now if this area decreases, this should increase. Just here the opposite case will be there. Okay, if m is less than 1, now here m is less than 1, say for example, then to equate these two, obviously if one side increases, the other side should decrease, this term should decrease. So if area decreases, the velocity should increase in the second case. If my flow is subsonic, so that's why it is written if the flow is subsonic and if the area of the duct decreases, the velocity will be increasing. Okay, that means if this is decreasing, area will be increasing. So here the duct acts like a nozzle. Okay, so here you see if the area decrease, here I have taken the same thing in the two cases, first case and second case, so that you can compare. So that means you see if area decreases, here it is written velocity increases, that means it acts like a nozzle. But here what is written, area decrease, that means the same duct, I am using the same duct, area decreases, but here I can see the velocity decreases. That means the same duct may act like a nozzle or the same duct may act like a diffuser, depending on what? Depending on the value of
Mach number.
Mach number. If I am having supersonic flow, then this converging duct will act like a diffuser. If I am having a subsonic flow, that means m less than 1, this same convergent duct would act like a nozzle. Very, very important concept. You will not get this concept in your book in this manner. That's why I am repeating again and again. Clear to all of you?
Mach number the deciding factor.
Yes, Mach number is the deciding factor. And you have to compare with this equation. Very simple equation. You have to just mathematically as well as physically, both the things are comparable over here. Okay. Clear up to this?
Yes, sir. Yes.
Okay. So next we are having some very important. I am having 10 minutes, so I will finish this slide today. So you see the concept that we have got here. I am having this type of a duct. Okay, converging diverging duct. What this type of duct is called? This is called a converging diverging duct, and this is the direction of the flow. You can see this picture clearly.
Yes, sir. Yes, sir.
Okay, so this is the throat, that is the minimum area. Okay, it is called throat of the duct, and this type of duct is the converging diverging duct. First part is converging, second part is the diverging, and in between we are having the minimum area. Now if I am trying to plot a graph between Mach number and x is in this distance, I am having in x direction, I am having the length, what will be the change in Mach number basically? Okay, the plot will be something like this. If m is greater than 1, that means if my flow is supersonic and if my flow is subsonic, then this will be the trend. This will be the trend of the plot. That means how the Mach number will change throughout the duct. That means my flow is obviously either my flow will be subsonic, either my flow will be supersonic, or my flow will be sonic. Okay, when my flow will be sonic, obviously it will be not changing. The middle one, this dotted line, will be the case. Okay, the graph between the Mach number and the length of the duct x. But these two cases, when I am having the supersonic case m greater than 1, when I am having subsonic case m less than 1, how the Mach number will change throughout the duct. Okay, now see here, you can just compare with the last slide that we have discussed. Okay, that means this part you can see it is my converging. Okay, it is my converging or not. Just try to correlate this
Yes,
part.
sir,
I
yes,
need
sir.
some response from your side. This part, first part,
Yes, sir.
is my converging. Okay,
Yes, sir.
and Mach number is greater than 1. That means this first part should act like what? Diffuser or nozzle?
Diffuser, sir. Yes.
Diffuser. That means my velocity will decrease, right? My velocity will decrease. So if my velocity is decreasing gradually up to this throat, then obviously my Mach number will decrease up to this throat or not. That's why it is decreasing, because Mach number is what? U by C. C is constant for a particular medium. Okay, so U is what? U is happening decreasing or not in the first part for your supersonic flow.
Yes.
Just in the last slide we have discussed
Yes,
the
sir.
same concept.
Definitely.
So that's why you can see there is a decrease, okay, up to this throat, and just the vice versa for the rest of the part. Okay, then it is increasing again the Mach number, because here I am having the flow is my supersonic flow, but my area is increasing. So if my area is increasing, then for supersonic flow it will be act like a nozzle. Okay, act like a nozzle means basically it is my the velocity will increase. Okay, like this. So in some cases the whole thing basically is called a convergent divergent nozzle also. Okay, basically why that is called, I'm telling you the reason. In some problem you may find that the convergent divergent nozzle. Okay, now how it can be a convergent divergent nozzle? Convergent divergent duct means this is the convergent divergent duct. Okay, when I can call it as a convergent divergent nozzle, the inlet velocity and the outlet velocity I have to see. If the outlet velocity is larger than the inlet velocity, then obviously that whole duct will be called as a nozzle. Got my point? When
Sir,
the whole
can you
duct,
please repeat once?
yes, I am repeating. You can see the convergent divergent duct over here. So in some problem it may be, that means some cases it is called convergent divergent nozzle. When the nozzle term comes, okay, that means you have to consider that the outlet velocity of that duct is greater than the inlet velocity of the duct. Inlet means this is the inlet, outlet means this is the outlet. Whatever I have shown over here, this is what is happening inside the duct. What is happening inside the duct, how the Mach number is changing inside the duct. But if this outlet point is say over here, that means it is much more divergent. Okay, that means my velocity will large, that means the velocity will be increasing more. Okay, just after the throw, that means the outlet velocity if larger than the inlet velocity, then obviously that whole duct should be called as a nozzle or not. The
Yes,
whole
sir.
duct
Yes.
should be called as a
Yes, sir.
nozzle.
The
That is the
velocity
concept.
increases by
Don't,
Yes.
okay, don't mix up with the all the concepts. Basically, when the whole duct will be called as a nozzle when my outlet velocity is greater than the inlet velocity. And why I have shown this one, because you have to understand how the Mach number is varying inside this duct. That's why I have shown. And just the vice versa for this subsonic flow, I am not discussing. Just the opposite will be there. How this trend should be clear to you. It is just the opposite for the supersonic flow. It is my subsonic flow. It will be just the opposite trend. Okay. So in this case, you can see it is my supersonic zone. It is my subsonic zone. Okay. The minimum cross section of a variable area duct is known as throat. I have already told that. If the entry condition of the flow is supersonic to a convergent divergent duct, the throat may have minimum value of m. But if the flow is subsonic throat, we will have the maximum m. Why I have shown this? Basically, you see, just I am reading out these lines again. You read this line again. If the entry condition of the flow is supersonic, that means this case m greater than 1. This is the convergent divergent duct. What will happen? The throat may have minimum value of M. Throat is having the minimum value of M or not for supersonic? Neither inlet nor outlet. Only the throat is having minimum value of your Mach number or not? Clear?
Yes,
This
sir.
point?
Yes.
It is
Yes,
very
sir.
much
Yes.
clear. It is very much clear from the graph. Now you correlate with that line that I told you. Take a note that practically that thing will happen at the minimum cross section. What is happening practically? Practically, this is happening at the minimum cross section. Okay, that Mach number is equals to, Mach number is the minimum value. Now Mach number is equals to 1. I am coming to that point. But if the flow is subsonic, that just this case, if I am having subsonic, obviously the throat will have the maximum value of M. These concepts are why important. These MCQs may come in your gate also, any type of your recruitment exams, whatever you give. Okay, concept of compressible flow is lying over here basically. Okay, the concept of nozzle, concept of diffuser, concept of how the your area is changing, Mach number is changing, how the velocity will change, everything is changing, but it is dependent. If you understand, if you don't try to memorize, you cannot memorize these things, you will mix up. Okay.
Sir, one question is there, sir.
Yes.
Sir, if the Mach number is less than 1, so is it becoming a divergent convergent nozzle?
No, Mach number, no, divergent, convergent actually doesn't exist. Basically, convergent, divergent exist. You see what is happening over here. You are asking about, if you try to understand this plot, what is happening for the subsonic flow. M less than 1, convergent duct, just in the last slide, what you have understood? M less than 1, convergent duct will act like a nozzle.
Yes, sir.
Right? So, nozzle means the velocity will increase or decrease. Velocity will increase. So,
Increase,
here,
yes.
so velocity is increase means Mach number will increase gradually or not?
Okay,
Mach
yes.
number is equals to U by C.
Yes.
C is constant for a particular medium. U is increasing for this part, first part, when I am having this subsonic flow. So that's why this Mach number is gradually increasing, you see. Okay, up to the throat. Up to which? Up to the throat. After the throat, what is happening? After the throat, I am having some divergent. Okay, so after the throat, again, just the opposite is happening. That means if the area decreases, then the velocity will also decrease. As the velocity is decreasing for the subsonic flow, in the rest of the part, my Mach number is also decreasing. Understood the trend?
Yes, sir. Yes.
Okay, so you have to keep in your mind everything so that you can understand it conceptually, not by theoretically only. So here, this thing you just see. In conclusion, what I can say, it should be mentioned that it is not necessary that at the throat of a variable area duct, Mach number will have the value of 1. Okay, this is basically wrong. If anyone says at the throat always Mach number is equals to 1, that is not true, because that is also not happening here. You can see it is not touching this M is equals to 1 line. It may not touch. That depends. It may touch, it may not touch. But if it touches, if it achieves the Mach number is equals to 1, that should be at throat. Okay, that is my point of concern. But if we have the value of Mach number is equals to 1, that should be at the throat of the duct, nowhere else. Okay, I am repeating again this line. Try to understand. It is not necessary that at the throat of a variable area duct, this is the variable area duct, this is the throat. Okay, it is not necessary that at the throat of a variable area duct, Mach number will have always the value of 1. Will have the minimum or the maximum depending on the type of flow, my supersonic or it is my subsonic. But if the Mach number is equals to 1 for a particular this type of duct is there, and I am saying that where Mach number is equals to 1 may occur, it should occur at throat, nowhere else. Got my point?
Yes, sir.
That means the reverse is true. That means this at the throat, always there is no hard and fast rule that always my Mach number is equals to 1 at throat. No. But if Mach number is equals to 1, this condition exists. That will exist where? In this convergent divergent duct, that will exist at this throat. That is the concept. Clear enough?
Yes, sir.
Okay. So that is basically the underlining concept over here. Yes, someone is asking something? Someone is asking anything? Okay, so that is basically the concept of this Mach number and convergent divergent duct, which correlates with the supersonic and subsonic flow. I think it is. I have tried my best to make it clear through this type of your drawings and this type of plots. so that in different manner you can understand the variations, okay, for a variable area duct. So this up to this,
ম্যাক নাম্বারের ওটা 1 হয় তাহলে ওটা মানে ছোটের সাথে ইয়ে হয়।
yes, ম্যাক নাম্বার যদি 1 হয় সেটা অলওয়েজ থ্রোটে হবে, নো হয় এলস, অন্য কোথাও হবে না, okay. If I am saying Mach number is 1 for a convergent divergent duct, where that will occur? That will surely occur at throat, okay. But it is opposite to true now. That means the opposite, if I say at the throat always Mach number is equals to 1, no, that is not true. That may not happen. That may be 1, that may not be 1. But if Mach number is equals to 1, that will be at throat. Is that clear? Okay. So that's why repeatedly I told these things. Okay. On the next class, we will discuss more about this Mach number and this area, all these things. You can see some more mathematical parts are coming, and we will enter to the nozzle. So, is there any doubt regarding this class?
No, sir.
Okay. Thank you.
No, sir.
And do you need this lectures, the recorded lectures, so that if you need, I can share it. Okay. I think Google Classroom is there already, right?
Yes, sir. Yes.
Okay. So I will share the recorded lectures at the evening or the night. Thank you. Okay.
sir.
So thank you for attending, and all of you have given the attendance in the last class.
Yes, sir.
Okay.
Yes, sir. Yes.
Okay. Okay. Thank you. Thank you very much. See you in the
Yes,
next
sir.
class.